are going to explain about the project titled Data-Driven Classification of Opioid Patients Using Machine Learning and Investigation. Introduction. This project centers on employing machine learning techniques to categorize opioid patients into distinct groups based on various parameters or features derived from data. The goal is to identify patterns or clusters within the data that can differentiate between different types of opioid users. The rising opioid crisis and the surge in drug overdoses have underscored the critical need for accurate methods to classify opioid users. Accurate classification can aid in early identification of at-risk individuals, optimize intervention strategies, and potentially reduce opioid-related harm. Prior research has not adequately delved into the relationship between mental health conditions and opioid consumption. This gap in understanding is significant given the potential correlation between mental health disorders and opioid use, which could impact treatment approaches and outcomes. This project aims to fill the void in existing research by leveraging machine learning and deep learning methods. These advanced techniques can analyze complex relationships within the data, potentially uncovering connections between mental health factors and opioid usage that might have been overlooked previously. The project uses the MIMIC Medical Information Mart for Intensive Care database, which contains both structured and unstructured data. This database is a valuable resource in healthcare research, providing comprehensive patient information, including clinical notes, demographics, medications, and more. The project employs traditional machine learning models alongside deep learning models to predict and distinguish between intentional and accidental opioid uses. This differentiation is crucial as it helps in understanding the circumstances and motivations behind opioid usage, aiding in tailored intervention strategies. Objective. The primary aim of the project is to employ machine learning techniques to categorize opioid patients into distinct groups. This categorization is based on analyzing various data-driven parameters, which could include demographics, medical history, dosage patterns, and other relevant factors available in the data. The project seeks to categorize opioid patients to create personalized treatment plans. These plans are designed to optimize pain management strategies, identify early signs of addiction risk, and tailor interventions according to the specific needs and characteristics of each subgroup identified through classification. Another objective is to develop predictive models capable of identifying patients at higher risk of opioid misuse or addiction. These models aim to forecast potential issues beforehand, enabling healthcare providers to intervene proactively or implement preventive measures, thus mitigating the risk associated with opioid use. By utilizing machine learning on extensive opioid and patient data, the project aims to uncover crucial insights. These insights are expected to reshape the understanding of opioid patients, their treatment needs, and support mechanisms within the healthcare system. This transformation leads to more effective, tailored, and supportive approaches for opioid patient care. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8GB and above, hard disk of 25GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing necessary libraries or packages in the programming environment. Commonly used libraries like Pandas, Matplotlib, Seaborn, and possibly others for data manipulation, visualization, and machine learning are imported here. These libraries provide tools and functions for data handling, analysis, and visualization. Exploring the dataset. Mimic multiple data. In this phase, the Mimic 3 dataset, which likely contains various tables or datasets related to patient information, is explored. This step involves loading the dataset into the environment and examining its structure, content, and features. Understanding the dataset is crucial before proceeding with data processing and analysis. Data processing. Pandas data frame. The dataset is converted into a Pandas data frame, a tabular data structure used in Python for data manipulation. Cleaning the dataset. This involves pre-processing the data to handle missing values, remove duplicates, correct inconsistencies, and perform other necessary data cleaning operations to ensure data quality. Concatenate the multi-data. If the dataset consists of multiple tables or sources, this step involves merging or concatenating them into a single comprehensive dataset for analysis. Dropping unwanted columns. Removing columns that are irrelevant or redundant for the analysis to streamline the dataset. Visualization using Seaborn and Matplotlib. Utilizing Seaborn and Matplotlib libraries, data visualization techniques are applied. This step includes creating various types of charts, plots, or graphs to visually explore relationships, distributions, trends, or patterns in the data. Visualization aids in understanding the data better and identifying potential insights. Label encoding. Label encoding is a technique used to convert categorical data, textual or non-numeric, into numerical format, allowing machine learning algorithms to interpret the data. This step assigns unique numerical labels to categorical variables, facilitating their use in machine learning models. Appending the feature column to X and target to Y. Features, independent variables, are appended to X, a variable that holds the input data for machine learning models. Y represents the target variable, the variable to be predicted, which is appended to another variable. Preparing X and Y in this way sets up the data for model training and evaluation. Splitting the data to train and test for deep learning and taking X and Y for machine learning. Splitting the data into training and testing subsets is a crucial step in machine learning. The training set is used to train the model, while the testing set is used to evaluate its performance. This step prepares data specifically for deep learning using X and Y and machine learning. Building the model. This step involves creating the structure of the machine learning or deep learning model. For deep learning, this involves defining neural network architecture, layers, activation functions, etc. For machine learning, it entails selecting algorithms, defining parameters, etc. Training the model with hyperparameter and k-fold cross-validation. Hyperparameter tuning involves optimizing the model by selecting the best parameters. K-fold cross-validation is a technique used to validate model performance by splitting the dataset into K subsets and training the model K times using different subsets has validation data each time. Comparing the result. After training and validation, the performance of different models or variations of the same model is compared. Metrics like accuracy, precision, recall, and FN score are used to evaluate and select the best performing model. Building the model with selected features with the highest accuracy score. This step involves constructing a refined model using only the features that contribute most significantly to accuracy. Feature selection is crucial for optimizing model performance and reducing complexity. Flask framework with SQLite for sign-up and sign-in. Flask is a Python web framework used for building web applications. In this context, Flask is likely used to create a web interface for user sign-up and sign-in functionality. SQLite, a lightweight relational database management system, is used to store user authentication data. User gives input as feature values. Users provide input data, feature values through the front-end interface created using Flask. These inputs will likely include information relevant to predicting opioid usage or related factors. The given input is pre-processed for prediction. The input data provided by the user is pre-processed in a similar way as the initial dataset. This step ensures consistency and compatibility with the model's requirements for making predictions. Trained model is used for prediction. The pre-processed user input is fed into the trained model, which uses its learned patterns to predict the outcome related to opioid usage or classification. Final outcome is displayed through front end. The predicted outcome or classification results obtained from the model are displayed to the user through the front-end interface, completing the prediction process and providing the user with relevant information or insights. Algorithms used in the project are random forest. Random forest is an ensemble learning method that constructs multiple decision trees during training and merges their prediction to improve accuracy and reduce overfitting. Random forests can be employed to classify opioid patients by considering various features in the dataset. Each decision tree in the forest assesses different aspects, and the collective predictions offer a more robust classification. AdaBoost. Adaptive boosting is an ensemble learning technique that builds a strong classifier by combining multiple weak classifiers in an iterative manner. AdaBoost can be used to iteratively train models, emphasizing misclassified instances in each iteration. In this project, it contributes to refining the classification of opioid patients by focusing on previously misclassified cases. XGBoost is an optimized gradient boosting algorithm that is highly efficient and often outperforms other boosting techniques. XGBoost is employed to enhance classification accuracy by sequentially building decision trees that correct errors made by preceding models. Its speed and performance contribute significantly to opioid patient classification. SVC, Support Vector Classifier. SVC is a supervised learning algorithm used for classification tasks. It finds the optimal hyperplane that best separates classes in high-dimensional space. SVC can be utilized to classify opioid patients by mapping data points into a higher dimensional space and identifying the optimal boundaries between different patient groups. Logistic regression. Logistic regression is a statistical model used for binary classification. It estimates the probability of a binary outcome based on one or more predictor variables. Logistic regression is employed to predict the likelihood of opioid misuse or addiction based on patient characteristics or features, providing probabilities for classification. ANN MLP, Artificial Neural Network Multilayer Perceptron. ANN with multiple layers, including an input layer, one or more hidden layers, and an output layer, used for classification or regression tasks. ANN MLP is utilized for complex pattern recognition in opioid patient data, with multiple layers of nodes processing information to classify patients into different groups. CNN, Convolutional Neural Network. CNN is primarily used for image recognition by extracting features through convolutional layers. However, it can also be adapted for sequence-based data. In the context, CNN is used if the project involves image data related to opioid usage or for sequence-based analysis of patient data. LSTM, Long Short-Term Memory. LSTM is a type of recurrent neural network RNN designed to handle sequence data by maintaining and using context information over long sequences. LSTM is applied if the project involves sequential patient data to capture dependencies and patterns over time for accurate classification. Attention LSTM. Attention mechanisms in neural network allow focusing on specific parts of the input sequence, enhancing model performance. Attention LSTM can improve the accuracy of sequence-based models like LSTM by dynamically weighting different parts of the patient data, potentially improving opioid patient classification based on relevant features. Ensemble methods combine predictions from multiple individual models to generate a more robust and accurate final prediction. The project's extension applies an ensemble method to merge predictions from various models to create a more reliable and accurate final prediction for opioid patient classification, leveraging the strengths of each model. Comparison graph. This is the accuracy comparison graph. On the x-axis we have the accuracy score, and on the y-axis we have the algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is a precision comparison graph. On the x-axis we have the precision score, and on the y-axis we have the algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis we have the recall score, and on the y-axis we have the algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis we have the FN score, and on the y-axis we have the algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is the model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I am copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I am typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, which is this localhost, and port, which is this, unless configured differently. Now we will copy this local link provided by the Flask framework. I am copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button. So here we need to enter all these details to register. But I have already registered, so click on sign in. So here we need to enter the username and the password which we have created, and then click on login. We have logged in successfully. So here we need to enter all these parameters and then click on predict. So I'm entering the parameters now. So here I have entered all the parameters. The first one is ethnicity. It is the demographic categorization of patients based on their ethnic or cultural background. So here the patient is Black or African American. Diagnosis 54, the specific medical condition or alignments for which patients are receiving treatment or care related to opioid use. Discharge location is home health care, the place where patients are released or transferred after their treatment or hospital stay. Insurance is Medicare, refers to the type of insurance coverage, private, government funded, uninsured, held by the patients. Gender is female, the categorization of patients based on their biological sex or gender identity. Marital status is separated, indicates whether patients are single, married, divorced, widowed, etc. Mental status is cognitive health, pertains to the psychological or psychiatric condition of the patient. LOS, length of stay is 1.6325, the duration for which patients remain admitted or receive treatment in a healthcare facility. Age category is 01 to 10. Age groups or ranges used to categorize patients. Example, young adults, middle-aged, elderly. ICD-9 is 3. The International Classification of Disease, 9th edition, codes used for diagnosing and documenting medical conditions. These parameters likely serve as key data points used to analyze and classify opioid patients through machine learning techniques for the purpose of understanding patterns, predicting outcomes, or optimizing treatment strategies. After entering all these parameters, click on Predict. So here we got the result. The patient is not dead based on the input provided. Now we will enter another set of parameters and check the result for one more patient. So I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on Predict. So here we can see we got the result. The patient is not dead based on the input provided. So in this way, by entering the inputs, we can predict whether the patient is dead or not. The conclusion of the project is summarizes the main findings derived from the classification of opioid patients. It emphasizes the subgroups or categories identified among these patients based on the data-driven analysis. These subgroups represent different patterns of opioid usage, demographics, risk factors, or other distinguishing features among patients. Understanding these subgroups is vital as it helps in tailoring interventions, treatments, or support strategies for each subgroup, thereby enhancing healthcare practices. This section of the conclusion focuses on the broader implications of the project's findings. It discusses how the insights gained from the classification of opioid patients impact healthcare practices, patient care, and management of opioid prescriptions. For instance, it might highlight how these insights lead to more effective treatment strategies customized for different patient subgroups, earlier identification of risk, or targeted interventions that address specific needs, ultimately improving patient outcomes and healthcare efficiency. Ablation analysis involves systematically removing or altering different components or parameters in a system to understand their individual impact on the overall performance. In this project, the ablation analysis likely explores how changes in specific components, features, or parameters affect the performance of the opioid patient classification system. This analysis helps in identifying the most influential factors contributing to the system's effectiveness, guiding future improvements or optimizations. The project aims to extract new insights into opioid patients, aiding to the existing knowledge in this field. By utilizing data-driven approaches, the project reveals previously unknown or underexplored aspects of opioid patient classification or behavior. These new insights contribute to advancing the understanding of opioid usage patterns, patient demographics, risk factors, or other relevant aspects, potentially leading to advancements in healthcare practices and policies related to opioid prescription and patient care.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Project's YouTube channel and subscribe.